93 million miles away, the blinding glare of our star conceals over 15,000 undocumented, city-killing asteroids. But the sheer mass of these hidden rocks isn't the anomaly exposing our planetary defense. The true threat approaches from the daylight side of our own planet. We scan the night sky while kinetic anomalies ride the sun's glare directly toward us. When the sky ignites without a single warning siren, what is the protocol for survival? We are entering a highly consequential window in the timeline of planetary defense. Not decades from now. Right now. By late 2026, humanity will capture its first proximity view of the near-Earth object Kamo'oalewa, and we will witness the arrival of the Hera spacecraft at the Didymos system, a battered, binary asteroid field serving as our premier testing ground for kinetic deflection. The passive observation of the cosmos is ending. The era of active, structural intervention has begun. However, to understand the mechanics of how we intend to stop a world-ending impact, you must first understand how these anomalies managed to slip past our early warning networks in the first place. The architecture of planetary defense relies on a single, fragile premise: optical contrast. To identify a near-Earth object, a lifeless, dark rock moving through the vacuum of deep space, astronomers require that object to be illuminated by the sun against the pitch-black canvas of the night sky. Ground-based observatories operate by capturing photons of sunlight that have traveled millions of miles, bounced off the rugged, carbon-rich surface of an asteroid, and reflected back into the lens of a telescope here on Earth. If that optical contrast is removed, the system fails. The data stops. The rock vanishes. This creates a massive, insurmountable blind spot stretching across the inner solar system. When an asteroid is interior to Earth's orbit, meaning its trajectory circles closer to the Sun than our own planet does, it spends the vast majority of its existence masked by daylight. Astrophysicists measure this problem using a metric called the solar elongation angle. This is the exact angular distance between a celestial object and the Sun, as viewed from your position on Earth. Think of solar elongation like standing on a dark highway, staring directly into the high-beam headlights of an oncoming semi-truck. Now, imagine a dark grey moth flying just a few feet in front of those headlights. You will never see the moth. The intense light completely saturates your retinas, erasing any faint reflection from the insect. You only see the glare. When an asteroid's solar elongation angle drops below roughly 45 degrees, it becomes the moth. It is swallowed entirely by the glare of our star. Our most advanced ground networks, such as the Pan-STARRS Observatory atop the Haleakala volcano in Hawaii or the Catalina Sky Survey in the Santa Catalina Mountains of Arizona, are engineering marvels. They utilize 1.5-meter mirrors and incredibly sensitive charge-coupled device (CCD) cameras that take rapid sequential images of the sky. A software algorithm then analyzes these images, searching for a single pixel moving across a stationary background of stars. A moving pixel is a rock, but these multi-million-dollar optical arrays are strictly constrained by the physics of light. They are constrained by atmospheric scattering. They are constrained by thermal noise. They are constrained by solar radiation. If astronomers were to point these sensitive CCD cameras anywhere near the Sun, the concentrated thermal energy would instantly vaporize their imaging sensors. Therefore, the observatories are forced to wait. They wait for the terminator line, the dividing boundary between day and night, to wash over their mountain peaks before they can safely open their shutters and begin scanning the void. But the asteroids are not bound by our planetary rotation. Consider the orbital mechanics of the Hera-class asteroids. Named after the first confirmed body of its kind, 163693 Hera, these anomalies possess an aphelion, their absolute furthest orbital point from the Sun, that is strictly less than 1 astronomical unit. This means their entire orbital path exists completely inside the orbit of Earth. They never venture out into the dark outer solar system. They are permanent residents of the daylight side. Because of this specific orbital geometry, an Hera-class asteroid can only be observed from Earth during a violently brief window, the roughly 15 to 30 minutes of twilight just after sunset, or just before dawn. During this narrow window, the Sun has dipped below the horizon enough to prevent the telescope sensors from burning out, but the sky is still low enough in solar elongation to catch the rock. Astronomers must point their telescopes low to the horizon, peering through the thickest, most turbulent layers of Earth's atmosphere, battling light distortion, moisture, and atmospheric refraction, hoping to catch a faint moving pixel before the sun rises and washes the sky out in blue. This 15-minute window is our entire defensive perimeter against daylight threats. We must be intellectually honest about the data. The sun is not generating a magnetic shield that hides these objects. The sun is not altering the trajectory of these rocks to target Earth. The science does not support any malicious cosmic coordination. The reality is far simpler and infinitely more consequential. The sun is simply outshining them. By relying almost exclusively on ground-based optical telescopes, we have inadvertently left a backdoor wide open. We are scanning the darkness behind us, while heavily armored, millions-of-ton kinetic threats are silently approaching us from the light. A catastrophic asteroid strike does not actually require the asteroid to strike the Earth. To completely erase a modern metropolis, a space rock never needs to touch the ground. When we imagine an impact event, our minds naturally default to the creation of a massive crater. We picture a hypervelocity bullet striking dirt, excavating millions of tons of bedrock, and leaving a permanent scar on the Earth's crust. But this is a fundamental misunderstanding of fluid dynamics and kinetic energy. For the vast majority of mid-sized near-Earth objects, the atmosphere itself acts as an impenetrable brick wall. Consider the entry velocity. An average asteroid intersects Earth's orbit traveling at an average velocity of 18 kilometers per second. That is over 40,000 miles per hour. At those speeds, the atmosphere ceases to behave like a gas. It behaves like a solid. As the rock plunges into the upper reaches of the atmosphere, it begins to push the air molecules out of its way. But at 18 kilometers per second, the air simply cannot move fast enough. The immense speed rapidly compresses the air directly in front of the asteroid, creating a massive buildup of force known as ram pressure. Ram pressure is not caused by friction. It is an adiabatic process, a direct consequence of countless air molecules being violently forced to occupy a smaller space. Think of a bicycle pump. When you push the handle down rapidly, the metal cylinder gets incredibly hot. You are forcing the same number of air molecules into a radically smaller volume. Now, scale that bicycle pump up to the size of a mountain, moving at hypersonic speeds. The ram pressure generates a superheated plasma shield on the leading edge of the rock, driving temperatures to extreme levels. But the heat is not what destroys the asteroid, the pressure is. Every rock has a structural limit. As the asteroid descends into the progressively thicker layers of the lower atmosphere, the ram pressure amplifies exponentially. Eventually, this invisible wall of compressed air exceeds the structural integrity of the rock itself. Fine tendrils of superheated air, essentially high-pressure plasma, force their way into microscopic cracks and faults on the asteroid's leading face. This is the exact moment of catastrophic failure. Once this plasma infiltrates the interior, it exerts tremendous pressure over a much larger internal surface area, acting exactly like wind suddenly filling a sail. From the inside out, the plasma violently forces the asteroid apart over a nearly instantaneous span of time. The rock shatters. In a fraction of a second, a single aerodynamic bullet is transformed into a rapidly expanding cloud of rubble. And this is where the laws of physics execute their grim mathematics. A single solid object, moving at 18 kilometers per second, carries an apocalyptic amount of kinetic energy. When that object is suddenly shattered by ram pressure, its mass ceases to move at orbital speeds. The rubble cloud hits the thick atmosphere and is abruptly halted. But that immense kinetic energy cannot just disappear. The conservation of energy demands a conversion. In an instant, the immense forward momentum is converted directly into an explosive release of heat and a concussive shockwave. This is an airburst. It is a disintegration occurring with a speed comparable to an explosive detonation, often yielding energy equivalents measured in megatons of TNT. It is functionally identical to the detonation of a thermonuclear warhead, completely blinding and intensely destructive, yet devoid of any chemical explosives or radioactive fallout. The explosion radiates outward, generating an overpressure wave capable of flattening forests, shattering concrete, and leveling city grids, all originating from a rock that completely disintegrated miles above our heads. To understand the absolute structural vulnerability of relying on a dark sky, we must examine the events of February 15, 2013. On that morning, A near-Earth object roughly 20 meters in diameter, about the size of a 6-story building, intersected Earth's orbit at a velocity exceeding 18 kilometers per second. It entered the airspace over the southern Ural region of Russia. It triggered no alarms. It triggered no sirens. It arrived in absolute silence. The reason for this intelligence failure was orbital geometry. The asteroid approached from the daylight side of the planet. Its trajectory was masked entirely by the sun's glare, rendering it physically invisible to every ground-based planetary defense telescope on Earth. We were completely blind. At approximately 9:20 a.m. local time, the atmospheric ram pressure, the invisible wall of compressed air we detailed in Part 2, overcame the structural integrity of the rock at an altitude of nearly 30 kilometers. The subsequent airburst released an estimated 500 kilotons of kinetic energy. This is not an abstract figure. It is the explosive equivalent of roughly 30 detonations of the atomic bomb dropped on Hiroshima, occurring instantaneously in the upper atmosphere. The flash of the detonation was, for a fraction of a second, 30 times brighter than the sun itself, casting rapidly moving shadows across the winter snow. But light does not shatter cities. The shockwave does. Minutes after the silent flash of light, the overpressure wave reached the ground. It struck the city of Chelyabinsk with crushing, indiscriminate force. It blew out the windows of over 7,000 buildings. It caused factory roofs to collapse. It sent nearly 1,500 people to the hospital, the vast majority suffering severe lacerations from a blinding citywide storm of flying glass. This was a 20-meter rock. In the categorization of planetary defense, a 20-meter object is considered mathematically insignificant. It is a microscopic grain of sand on the cosmic scale, yet it managed to deliver half a megaton of explosive yield directly over a populated metropolis, and humanity did not possess a single second of advanced warning. We must discard the assumption that destruction arrives as a massive glowing mountain detected years in advance. The Chelyabinsk precedent established a consequential, undeniable truth. The most immediate threat to human infrastructure is not the continent-killing Leviathan. It is the small, dark, undocumented anomaly that uses the sun as a shield. In 2005, the United States Congress legally mandated the National Aeronautics and Space Administration to detect, track, and catalog 90% of all near-Earth objects exceeding 140 meters in diameter. We are failing. The mathematical threshold of 140 meters was not chosen arbitrarily by politicians. It represents the precise inflection point where a kinetic strike transitions from a localized atmospheric disaster into an event of catastrophic regional devastation. Astrophysicists classify rocks of this magnitude as potentially hazardous objects, or PHOs. A PHO is not an abstract astronomical concept. It is a highly concentrated mass of rock or metal on an intersecting orbit with Earth, large enough to bypass total atmospheric fragmentation and violently reshape the geography of a continent. To put this into structural terms, a 140-meter asteroid is slightly larger than a professional football stadium. It carries the kinetic equivalent of a multi-megaton nuclear exchange. It will not cause the mass extinction of our species. It will simply erase a major metropolis, incinerate the surrounding ecosystems, and collapse the economic infrastructure of an entire hemisphere. The data is unyielding. NASA estimates the total population of these 140-meter anomalies currently orbiting our Sun to be approximately 25,000. They are scattered across the inner solar system, silently traversing the vacuum of space. To date, our global network of observatories has successfully catalogued roughly 43% of this population. The remaining 57% represents an unprecedented structural vulnerability. More than 14,000 massive city-killing asteroids remain entirely undiscovered, unmapped, and unaccounted for. Imagine navigating a heavily populated transport ship through a dark ocean known to contain 25,000 active naval mines. Your radar has successfully located 10,000 of them. The remaining 15,000 are physically invisible to your senses, drifting silently on the ocean currents. You know they exist, you know their destructive yield. You simply do not know their coordinates. Every single time the Earth completes an orbit around the Sun, we are sailing blindly through that exact minefield. The absence of optical confirmation is not evidence of safety. The fact that we have not yet detected an incoming 140-meter rock does not alter the absolute probability of its existence. We are staring into a statistical void. The threat is constant. The math is unforgiving. The impact date is simply unknown, and as the historical record proves, even when our early warning systems finally register a threat, the alarm often sounds when the rock is already at our door. In the theater of planetary defense, theoretical vulnerabilities mean nothing until they manifest as real-world data. We do not have to hypothesize about the catastrophic potential of a daylight blind spot. We lived it on July 13, 2023. On that Thursday, an undocumented anomaly designated as 2023 NT1 intersected our planet's immediate orbital neighborhood. It was a solid mass of rock, measuring approximately 30 meters in diameter. Had its trajectory intersected our atmosphere, it carried the kinetic yield necessary to cause significant local damage and erase a modern city center. It passed our planet at a distance of roughly 100,000 kilometers. To comprehend that distance, you must look at our own moon. The moon orbits Earth at an average distance of 384,000 kilometers. Asteroid 2023 NT1 severed that distance, flying nearly 4 times closer to us than our only natural satellite. Moving at velocities exceeding 15 kilometers per second, it plunged deep into our localized gravity well. It penetrated our inner defensive perimeter. It triggered zero alarms. Our global network of early warning observatories, specifically designed, funded, and operated to prevent this exact scenario, registered absolutely nothing during the inbound approach. Because the asteroid approached from the daylight side of the Earth, the exact trajectory was masked by our star. It was a dark rock flying out of the sun's glare, entirely hidden from the optical arrays pointing toward the night sky. The rock was a ghost. It was not until July 15, a full 48 hours after the asteroid had already completed its close approach and was flying safely away from Earth into the dark vacuum of space, that the Atlas Observatory Station in South Africa finally detected a moving pixel on its monitors. This is the unprecedented structural reality of our current architectural framework. When a 30-meter kinetic threat flies closer to Earth than our own moon, you expect the scientific community to issue a warning. You expect a coordinated international tracking effort. You expect time to brace. Instead, astronomers were forced to issue a post-mortem. The delayed detection of 2023 NT1 was not a triumph of our surveillance networks. It was a mathematical autopsy. It unequivocally proved that if the asteroid's trajectory had been shifted by a mere fraction of a degree, the first indication of its existence would not have been a digital alert from a ground-based telescope. The first indication would have been the hyper-compressed wall of atmospheric ram pressure shattering the rock in the sky, instantly converting its mass into a blinding airburst over a populated center. We are not just failing to map the deep space threats, we are completely missing the ones grazing our own atmosphere. When a new kinetic threat is identified in the deep, the public expects a definitive answer. We demand a simple binary. Will it hit us or will it miss? But orbital mechanics do not operate in absolutes. They operate in the volatile, highly fluid calculus of probability. To understand how a threat level can drastically escalate and completely vanish within a single month, we must examine the unprecedented trajectory of asteroid 2024 YR4. Discovered on December 27, 2024 by the Atlas Network in the mountains of Chile, 2024 YR4 was initially classified as a massive anomaly, with early estimates suggesting a diameter between 40 and 90 meters. It is roughly the volume of a 15-story building. Upon initial detection, automated warning systems flagged a highly concerning orbital path, registering a potential impact with Earth on the exact date of December 22, 2032. This is where the mathematical architecture of planetary defense takes over. When an observatory detects an asteroid, it does not capture a high-definition video of its exact path. It captures a few disconnected data points, fleeting pixels of light against a dark background. Astronomers must extrapolate a complete orbital loop spanning hundreds of millions of miles from these microscopic breadcrumbs. Because the initial data is inherently limited, the resulting projected orbit is not a single razor-thin line. It is a massive, three-dimensional cone of mathematical guesswork, known as an uncertainty region. Think of a sniper firing a bullet in a pitch-black room. You hear the gunshot, and you know the general direction the barrel was pointing. You cannot predict the exact millimeter the bullet will strike the wall, but you can draw a wide circle on the wall representing every possible place the bullet could land based on the angle of the sound. That circle is the uncertainty region. As days passed in early 2025, more observatories locked onto 2024 YR4. They fed new telemetry data into the global models. As the data increased, the uncertainty region began to shrink. The cone narrowed. But as the cone narrowed, it did not shift away from Earth. It localized directly over us. By February 18, 2025, the probability of 2024 YR4 impacting Earth surged to 2.8%. In the highly conservative realm of astrophysics, a nearly 3% probability of a city-killing impact is not a mathematical curiosity. It is a structural emergency. It attracted the immediate attention of the global planetary defense community. But just as quickly as the threat localized, the calculus shifted again. A critical observation from the Very Large Telescope in Europe provided a microscopic refinement to the asteroid's orbit. That tiny fraction of new data altered the long-term forecast. The uncertainty region bypassed Earth entirely. We were safe. But the crisis was not over. The cone had simply shifted to our nearest neighbor. Revised calculations revealed a startling 4.3% probability that 2024 YR4 would slam directly into the Moon. A rock of this magnitude, impacting the lunar surface at hypervelocity, would excavate a crater roughly 1 kilometer wide. It would trigger a magnitude 5.0 moonquake, the strongest ever recorded. Millions of pounds of lunar bedrock would be violently ejected into space, with a significant fraction caught by Earth's gravity, raining down on our atmosphere as a massive meteor shower. For nearly a year, the planetary defense community watched this lunar impact probability hold steady. We were locked in a statistical standoff. The definitive resolution only arrived in February 2026. Scientists aimed the James Webb Space Telescope directly at the anomaly, using its highly sensitive near-infrared camera to track the faint object. By capturing this precise thermal data, astronomers were able to completely collapse the uncertainty region into a single, definitive line. The data confirmed that 2024 YR4 will not strike the Moon. It will thread the needle, passing safely at an altitude of 13,200 miles. The case of 2024 YR4 proved that the mathematics of planetary defense work. When given enough time and enough telescopic power, we can refine a terrifying anomaly into a harmless flyby. But the process relies entirely on a single, highly constrained resource: time. To calculate an uncertainty region, we need weeks of continuous observation. If an anomaly approaches from the Sun's blind spot, or is detected with only days to spare, the mathematics cannot save us. The bullet simply arrives before the math is finished. The fundamental flaw in our current planetary defense architecture is an over-reliance on visible light. Optical telescopes require a celestial object to reflect sunlight back to Earth. But many of the most dangerous anomalies in our solar system do not reflect light. They absorb it. Astrophysicists measure an object's reflectivity using a metric called albedo. A perfect mirror has an albedo of 1.0. Fresh snow has an albedo of roughly 0.8. Many carbon-rich, city-killing asteroids have an albedo of 0.04. This means they absorb 96% of all visible light that strikes their surface. They are essentially flying mountains of charcoal against the infinite black backdrop of deep space. Attempting to spot a 140-meter charcoal briquette using an optical telescope is mathematically futile. You cannot see the darkness, but the laws of thermodynamics offer a critical advantage. When a dark asteroid absorbs 96% of the sun's visible light, that massive influx of energy does not simply vanish. The rock heats up. As the surface temperature rises, the asteroid begins to radiate its own energy back out into the void. It does not emit visible light. It emits thermal radiation in the mid-infrared spectrum. To find the missing 60% of the 140-meter population, we must stop looking for reflections. We must hunt for the heat. This is the exact mandate of the Near-Earth Object Surveyor. Currently undergoing final fabrication and scheduled to launch in September 2027, NEO Surveyor represents the single most consequential shift in the history of planetary defense. It is a 50-centimeter space telescope specifically engineered to bypass the limitations of ground-based optics. Because Earth's own atmosphere absorbs the vast majority of incoming infrared light, NEO Surveyor cannot operate on the ground. It cannot even operate in low Earth orbit. where the intense heat radiating from our own planet would blind its sensitive instruments. Instead, the spacecraft will be positioned nearly 1 million miles away at a gravitationally stable location known as the Sun-Earth L1 Lagrange point. From this deep space vantage point, operating in a permanently cold thermal environment, the telescope will deploy its hypersensitive infrared detectors. These sensors are calibrated to capture wavelengths between 4 and 10 micrometers, the exact frequency of the thermal glow emitted by sun-warmed space rocks. NEO surveyor does not care about albedo. It does not matter if an asteroid is as dark as soot or as bright as ice. It does not matter if the rock is approaching from the blinding glare of the sun. If the anomaly possesses a temperature, NEO surveyor will detect its thermal signature. The mission is designed to achieve the congressional mandate of cataloging the vast majority of the missing 140-meter threats within a decade of operation. It will finally peer into the sun's blind spot. But until September 2027, the blind spot remains open. We are still relying on optical contrast. We are still waiting for the dark rocks to cross the terminator line. In April 2016, the Pan-STARRS optical network in Hawaii detected an anomaly locked in a deeply unusual trajectory. Designated 469-219 Kamo'oalewa, it is a solid mass of rock roughly 50 meters in diameter, but its orbital mechanics entirely defy the standard classification of a near-Earth asteroid. It is not simply flying past us, it is tethered to us. Kamo'oalewa is mathematically defined as a quasi-satellite. It is trapped in a one-to-one orbital resonance with Earth. To understand this, you must separate the visual from the physical. Kamo'oalewa does not orbit the Earth, it orbits the Sun. However, it is locked in a gravitational dance that forces it to complete its solar orbit in the exact same 365-day timeframe that we do. From our vantage point on the ground, this resonance creates an optical illusion. It appears to endlessly loop around our planet in a chaotic corkscrew pattern, never getting closer than 9 million miles, but never possessing the kinetic energy to fully escape our gravitational influence. It is essentially a ghost moon. It circles in the dark, but the geometry of its orbit is not the impossible fact. The impossible fact is its composition. When astrophysicists isolate the light reflecting off Kamo'oalewa's surface, they use a technique called reflectance spectroscopy. By breaking the light down into specific wavelengths, they can read the chemical signature of the rock, exactly like scanning a barcode. Standard near-Earth asteroids display barcodes heavy in carbon, iron, or nickel. Kamo'oalewa does not. Its spectral barcode is entirely anomalous for a deep space object. The light signature is a flawless, undeniable match for the specific silicates found in the rocks, brought back by the Apollo missions. It is not a captured asteroid. It is a piece of our own moon. We must be exceptionally clear about the data. The science does not suggest that Kamo'oalewa poses an impact threat to Earth. Its chaotic orbital resonance is mathematically stable for millions of years. It will not hit us. But the structural implications of its existence represent a profound warning regarding the kinetic environment of our immediate solar system. To create Kamo'oalewa, a massive undocumented asteroid had to strike the lunar surface with catastrophic precision. Recent structural modeling points directly to the Giordano Bruno crater, a 22-kilometer-wide impact scar on the far side of the Moon created a few million years ago. The inbound rock struck with such incomprehensible kinetic violence that it fractured the lunar bedrock, accelerated a 50-meter chunk of solid mass beyond the Moon's escape velocity, and ejected it permanently into a solar orbit. Kamo'oalewa is not just a celestial curiosity, it is lunar shrapnel. It stands as a permanent physical record of a city-killing impact occurring perfectly within our own orbital neighborhood. It proves that the void around us is not empty. It is a shooting gallery. And right now, in late 2026, humanity is executing an unprecedented maneuver to reach out and touch this shrapnel directly. Right now, millions of miles deep in the void of the inner solar system, an autonomous spacecraft is executing a flawless interception. In May 2025, China launched the Tianwen-2 probe atop a Long March 3 billion rocket from the Xichang Satellite Launch Center. It was aimed not at a distant planet, but at our immediate orbital neighborhood. As we move through the spring of 2026, Tianwen-2 has traveled tens of millions of kilometers and is initiating its final approach to the ghost moon, Kamo'oalewa. It is a mission defined by unprecedented navigational extremity. We are not attempting to orbit a massive stationary sphere. Kamo'oalewa is microscopic on the cosmic scale. It is a heavily space-weathered rock roughly 50 meters in diameter, tumbling rapidly through the vacuum with a rotation period of just 28 minutes. It possesses virtually zero gravitational pull. Imagine attempting to parallel park a compact car next to a rapidly spinning boulder. Now, remove your hands from the steering wheel. Finally, both you and the boulder are traveling at tens of thousands of miles per hour through a pitch-black abyss. That is the physics of the Tianwen. To arrival. Because the spacecraft is operating millions of miles from Earth, the communication delay is a structural barrier. The ground control teams cannot fly the probe with a joystick. Every single maneuver, from orbit insertion to the final terrifying descent, must be executed autonomously by the probe's onboard computers. It has to think for itself in the dark. Tianwen-2 will deploy a suite of 11 distinct scientific instruments, including specialized radars, spectrometers, and optical cameras. In mid-2026, the spacecraft will begin a methodical, highly dangerous descent, dropping its orbital altitude from a cautious 20 kilometers down to a staggering 300 meters from the asteroid's jagged surface. It will analyze the surface regolith, scan for S-type silicates or lunar ejecta, and map the precise structural fault lines of the rock. This is not simply a scientific flex. It is a mandatory structural prerequisite for planetary defense. We cannot deflect what we do not understand. If humanity is to ever deploy kinetic impactors against an incoming city killer, we must first learn how a spacecraft interacts with these microgravity anomalies at extreme proximity. Tianwen-2 is our proving ground, but mapping Kamo'oalewa is only the first phase. The probe is not just designed to observe, it is designed to make physical contact. The fundamental barrier to interacting with Kamo'oalewa is not the millions of miles we must cross, nor the rapid chaotic rotation of the rock itself. The barrier is mass. The asteroid simply has none. Because the object is estimated to be a mere 40 to 100 meters in diameter, its gravitational field is mathematically minuscule. Astrophysicists measure an object's gravitational hold using escape velocity, the exact speed required for a projectile to permanently break free from a celestial body's grip. On Earth, a rocket must achieve 11.2 kilometers per second to escape. On Kamo'oalewa, the escape velocity is measured in fractions of a meter per second. A human astronaut could achieve orbital escape simply by jumping. Therefore, the Tianwen-2 spacecraft cannot land. Gravity refuses to hold it down. If a multi-ton automated probe descends and attempts to rest its mass on the solid surface, the kinetic energy of that microscopic impact will instantly push the spacecraft backward into the void. Sir Isaac Newton's third law guarantees it. Every action demands an equal and opposite reaction. The probe will strike, the rock will resist, the probe will bounce. This creates an unprecedented structural dilemma for planetary defense. If we wish to understand the internal structural integrity of an anomaly, we cannot simply brush the exterior dust. We require deep, unweathered, physical samples. We need to drill. But drilling requires immense, sustained physical leverage. Think of attempting to push a heavy, motorized power drill into a solid concrete wall while standing on a frictionless sheet of ice. The drill bit spins, you apply forward pressure, and the wall immediately pushes you backward. You slide away. You cannot penetrate the wall without friction anchoring your feet. To solve this exact physics problem in the dark, aerospace engineers designed a novel architectural solution, the anchor and attach method. As Tianwen-2 matches the tumble of the asteroid and approaches the surface, it will not deploy traditional landing pads. It will deploy highly specialized drills. The exact instant the probe makes physical contact with the asteroid's regolith, the outer layer of loose, fragmented dust and rock covering the solid core, it will aggressively fire these anchors directly into the anomaly. The anchors are designed to penetrate. They bite, they lock. Once physically tethered to the asteroid, the spacecraft ceases to be a separate object. It becomes an artificial extension of the rock itself by pulling itself tight against the surface. Tianwen-2 artificially generates the friction and downward force that Kamo'alewa's near-zero gravity cannot provide. Only after this violent anchoring sequence is secure can the primary sampling phase activate. The probe will attempt to extract up to 100 grams of pristine material from beneath the space-weathered exterior, gathering invaluable data on the structural composition of the suspected lunar fragment. Because the regolith is entirely uncharted, the anchoring system must be exquisitely sensitive to the precise mechanical properties of the surface to maintain its grip during the entire operation. This mechanism is not merely an engineering flex. It is a mandatory structural precedent. If a city-killing asteroid is detected on a collision course with Earth, and humanity is forced to physically attach a nuclear ablation device or a sustained thruster to its surface, we will face the exact same physics. We will have to physically tie our survival to a rock that actively resists our grip. Tianwen, too, is currently testing the rope. Why endure the excruciating mechanical danger of anchoring to a rock in deep space? The objective is not simply to bring a cosmic artifact back to Earth. The mission is structural. The mission is survival. The mission is planetary defense. Grabbing a piece of an asteroid is the absolute prerequisite to understanding how these anomalies react to kinetic trauma. When you strike an object at high velocity, the physical outcome is dictated entirely by its material science. Physicists measure this interaction using a metric known as acoustic impedance. It is the exact mathematical resistance a material offers to a propagating mechanical wave, such as the shock wave generated by a hypervelocity impact. Think of swinging a heavy steel sledgehammer directly into a solid iron anvil. The hammer bounces violently backward. The anvil absorbs the shock. The energy transfers efficiently through the dense, uniform metal, and the anvil physically moves. Now imagine swinging that exact same sledgehammer with the exact same force into a massive mound of loose sand. The hammer does not bounce. It sinks. The sand absorbs the kinetic energy, instantly dampening the shockwave and scattering the force among millions of disconnected grains. The mound barely moves. Asteroids behave the exact same way. If our automated networks detect an inbound 140-meter kinetic threat and we launch a spacecraft to physically deflect it, we must know what we are hitting before the launch sequence begins. If the asteroid is a dense, metallic monolith, a solid chunk of iron and nickel forged in the early solar system, a kinetic strike will behave like the anvil. The energy transfers, the rock moves. We alter its trajectory and save a targeted continent. But if the asteroid is highly porous, the physics completely invert. Many of these anomalies are not solid rocks at all. They are fragile, gravity-bound clumps of dust, pebbles, and massive void spaces. If we strike a porous anomaly, it will behave like the sand. The impactor will bury itself into the regolith. The energy will be absorbed, violently localized, and dissipated into the empty spaces. The orbital trajectory will not change. The rock will simply absorb our best defense and continue its path toward Earth. The alternative is even more destructive. An improper strike on a fragile structure could trigger catastrophic fragmentation. Instead of moving the bullet, we risk shattering it. If the structural integrity of the asteroid fails upon impact, we would inadvertently transform a single, predictable kinetic event into a hypervelocity shotgun blast. The massive rock would break apart, spreading the threat across thousands of miles, raining localized destruction down across multiple hemispheres simultaneously. This is why deep space material science is non-negotiable. We cannot treat every asteroid as a uniform threat. Some are solid iron, some are silicate fragments, some are empty voids held together by microscopic gravity. Until we secure physical samples from these anomalies, we are guessing at the structural integrity of our targets. We are firing blindly into the dark. And in the mathematics of planetary defense, a guess is an unacceptable point of failure. In the history of our species, we have only ever been passengers on this planet, bound entirely to the gravitational currents of the solar system. We observed the sky, we catalogued the threats, we waited for the math to play out. That era ended on September 26, 2022. On that Monday, the National Aeronautics and Space Administration transitioned humanity from a passive target into an active structural force. The mission was designated the Double Asteroid Redirection Test, or DART. Its objective was not to collect regolith. Its objective was not to map a surface. The objective was profound, violent, and unprecedented. We launched a spacecraft to intentionally crash into a celestial body to see if we could physically move it. The target was a binary asteroid system. The primary body, Didymos, is a massive mass of rock, spanning roughly 780 meters across. Orbiting this primary body is a smaller, secondary moonlet named Dimorphos, measuring approximately 160 meters in diameter. To alter the trajectory of Dimorphos, aerospace engineers relied on a strategy known as the kinetic impactor technique. Stripped of its academic jargon, this is the cosmic equivalent of firing a bullet to deflect an incoming bullet. The mathematics rely entirely on the violent transfer of raw momentum. The DART spacecraft was not a massive, heavily armored battering ram. It was a box slightly smaller than a standard vending machine. It weighed roughly 600 kilograms. Against the millions of tons of solid mass that composed Dimorphos, the spacecraft was mathematically microscopic. But mass is only half of the kinetic equation. The other half is velocity. When the spacecraft initiated its final autonomous terminal phase, it was traveling at a staggering 22,500 kilometers per hour. That is roughly 6 kilometers per second. At precisely 23:14 Universal T, the DART probe slammed directly into the center of the moonlet. The physical destruction of the spacecraft was instantaneous. But the kinetic energy it carried did not vanish. It violently transferred directly into the bedrock of the asteroid. Before the impact, Dimorphos required exactly 11 hours and 55 minutes to complete a single orbit around its larger parent body. To declare the test a success, NASA established a highly conservative baseline. They calculated that if the impact could shave just 73 seconds off that orbital period, the kinetic deflection strategy would be considered mathematically viable for future planetary defense. Astronomers pointed the global network of telescopes at the debris cloud and waited for the orbital clock to reset. When the data returned, it completely shattered the baseline predictions. The DART impact did not shorten the orbit by 73 seconds. It reduced the orbital period by an astonishing 33 minutes. The sheer violence of the collision excavated a massive crater, ejecting millions of pounds of rocky debris out into the vacuum of space. This expanding plume of ejecta acted exactly like a massive temporary rocket thruster, dramatically amplifying the total momentum transferred to the rock. The impact was violent. The asteroid was pushed backward. Its orbit tightened. We must let the gravity of this data settle. For the first time in the 4.5 billion year history of the solar system, a biological species successfully reached out and measurably altered the orbital mechanics of a celestial body. We proved that the kinetic paradigm works. We proved that if a 140-meter city killer is detected with enough lead time, we possess the mathematical capability to knock it off course. But DART was only half of the equation. We fired the bullet. We proved the rock moved. Now, we must travel back to the crime scene to measure exactly how deeply the bullet penetrated. When planning the DART kinetic impact, astrophysicists faced a severe observational barrier. Deflecting a solitary asteroid orbiting the Sun presents a massive problem of scale. If we launch a kinetic impactor into a lone, dark rock, traveling in an orbit that spans hundreds of millions of miles, the initial deflection is mathematically microscopic. It would take ground-based telescopes years, potentially decades, of continuous optical monitoring to confirm if the orbital shift was successful. In the theater of planetary defense, we do not have decades to wait for the math to resolve. Furthermore, experimenting on a solitary asteroid carries an unacceptable existential risk. By intentionally altering the trajectory of a lone rock, we could inadvertently push it onto a new orbital path, one that mathematically intersects with Earth a century in the future. We could accidentally engineer our own extinction event. To solve this dual crisis of measurement and safety, the architectural planners required a highly specific cosmic geometry, a binary asteroid system. The primary body, Didymos, is a massive 850-meter-wide mountain of ancient rock. Bound to it by gravity is Dimorphos, a much smaller, 170-meter-wide moonlet. Dimorphos is the exact structural size of a city-killing kinetic threat. This binary configuration operates as a perfect, self-contained laboratory in the deep. Dimorphos does not independently orbit the Sun. It is gravitationally tethered, circling its parent body and completing one revolution every 11 hours and 55 minutes. Because this system is aligned with Earth's line of sight, telescopes on the ground can observe the moonlet passing directly in front of and behind the larger parent asteroid. Every time Dimorphos transits, it physically blocks a microscopic fraction of Didymos's reflected sunlight. This creates a predictable, rhythmic dimming on our astronomical sensors. It is a cosmic clock. It is a flawless metronome ticking in the void. By targeting the moonlet instead of a solitary rock, NASA completely isolated the kinetic experiment. The goal was not to violently alter the massive multi-year orbit of the binary pair around the Sun. The goal was simply to strike the moonlet and measure the disruption to the 12-hour localized clock. If the impact was successful, the moonlet's orbit would tighten. The dimming would occur faster. The metronome would skip a beat. This structural decision allowed scientists to explicitly measure the exact momentum transfer of the DART impact within days of the collision, utilizing existing ground-based telescopes, tracking the light curve. It entirely removed the risk of accidentally weaponizing an asteroid's solar orbit. It proved that planetary defense could be tested safely, efficiently, and with immense mathematical precision. But the unprecedented success of the measurement immediately revealed a sobering new anomaly. The clock changed drastically, but it changed because the asteroid's structural integrity was not what we thought it was. The mathematical success of the DART impact was undeniable. But as the dust cleared from the Didymos system, the telemetry data returned an unprecedented structural anomaly. Dimorphos was not a solid mountain of rock. It was a cosmic ball pit. Prior to the collision, planetary defense models largely treated the moonlet as a rigid monolith. However, the final images transmitted by the spacecraft's camera, captured mere milliseconds before its own annihilation, exposed a surface densely packed with massive, shipping container-sized boulders. The data confirmed that Dimorphos is what astrophysicists classify as a rubble pile asteroid. This is a critical distinction in materials science. A rubble pile is not a singular geologic body. It is a fragile fleet of disconnected debris, gravel, and dust, barely held together by an incredibly weak gravitational field. There is no continuous bedrock. There is no structural permanence. It is loosely bound. When the 600-kilogram impactor struck this porous cluster at roughly 6 kilometers per second, it did not simply carve a clean crater into a hard surface. The physics completely inverted. The spacecraft plunged deeply into the loose material, violently excavating over 1 million kilograms of rocky debris and ejecting it out into the vacuum of space. This massive spray of displaced mass acted exactly like a chemical rocket thruster, generating a physical phenomenon known as the momentum enhancement factor. The debris carried its own kinetic energy away from the asteroid, effectively doubling the physical punch of the spacecraft itself. The ejector amplified the force. The ejector altered the orbit. The ejector fundamentally deformed the asteroid. Because Dimorphos lacked a solid, rigid interior, the immense kinetic trauma of the impact caused the rock to behave essentially like a fluid. The sheer violence of the collision triggered global resurfacing. The asteroid physically warped, transitioning from a roughly symmetrical sphere into a flattened, chaotic oval. The rock absorbed the shockwave, shifted its internal mass, and swallowed the blow. This structural revelation introduces a highly consequential dilemma for future planetary defense. If a 140-meter city-killing threat is detected, and our analysis confirms it is a loosely bound rubble pile, the kinetic impactor strategy becomes exceptionally volatile. If we strike a fragile structure too aggressively, the energy will overmatch the microscopic gravity holding it together. The anomaly will not simply deflect, it will shatter. By applying too much kinetic force, we risk transforming a single, mathematically predictable bullet into a massive, uncontrolled swarm of hypervelocity shrapnel raining down across multiple continents. The DART experiment proved we can move a moonlet, but it also proved we barely understand the structural integrity of the objects we are targeting. We are firing blind. When NASA's DART spacecraft annihilated itself against the surface of Dimorphos in 2022, it was essentially a hit and run. We fired a highly instrumented bullet into the dark, recorded the exact moment of catastrophic impact, and watched the orbital clock shift from Earth. But ground-based observatories are fundamentally blinded by distance. They can measure the rhythm of the dimming light, but they cannot see the physical rock. We know the moonlet moved. We do not know how deeply it bled. To transition the kinetic deflection strategy from a one-time experiment into a repeatable, globally standardized defense protocol, we require forensic certainty. We need to measure the exact dimensions of the impact crater. We need to calculate the precise structural deformation. Above all, we need mass. Without knowing the exact mass of the rubble pile before and after the collision, the kinetic momentum equation remains a heavily estimated variable. In planetary defense, An estimation is a structural vulnerability. This is the precise mandate of the European Space Agency's Hera mission. Launched in October 2024, the Hera spacecraft has spent the last 2 years silently traversing tens of millions of miles of deep space vacuum. Right now, moving through late 2026, it is executing its final complex rendezvous maneuvers to match the orbital velocity of the Didymos binary system. It is arriving at the cosmic crime scene. Hera is not a blunt force impactor. It is a highly sophisticated orbital detective. Roughly the size of a compact vehicle, the spacecraft is equipped with a comprehensive payload of high-resolution optical cameras, thermal infrared imagers, and laser altimeters. As Hera inserts itself into a deeply complex chaotic orbit around the binary pair, it will systematically map the dimorphous anomaly down to the resolution of a single meter. It will scan the surface. It will measure the crater. It will calculate the mass. This sustained proximity operation requires unprecedented navigational autonomy. Because the collective gravitational pull of the Didymos system is astronomically weak, Hera cannot simply lock into a traditional circular orbit like a telecommunications satellite circling Earth. It must perform a continuous sequence of precise, thruster-controlled, hyperbolic arcs. It must constantly adjust its trajectory to avoid drifting away into the solar void, while simultaneously ensuring it does not accidentally collide with the jagged, unstable debris field still lingering around the shattered moonlet. The DART impact proved that humanity possesses the raw kinetic force to push a celestial body off its axis, but raw force without precise calculation is strategically useless. If a 140-meter city killer is detected with only 5 years of lead time, we will not have the luxury of running a preliminary test. We will only get one shot. We must know exactly what size mass to launch, at what velocity, to achieve the exact orbital shift required to clear our atmosphere. Hera is the mathematical key. It is currently decelerating in the dark, preparing to illuminate the wreckage and finalize the exact equation for human survival. When NASA's DART spacecraft annihilated itself against the surface of Dimorphos in 2022, it was essentially a hit and run. We fired a highly instrumented bullet into the dark, recorded the exact moment of catastrophic impact, and watched the orbital clock shift from Earth. But ground-based observatories are fundamentally blinded by distance. They can measure the rhythm of the dimming light, but they cannot see the physical rock. We know the moonlet moved. We do not know how deeply it bled. To transition the kinetic deflection strategy from a one-time experiment into a repeatable, globally standardized defense protocol, we require forensic certainty. We need to measure the exact dimensions of the impact crater. We need to calculate the precise structural deformation. Above all, we need mass. Without knowing the exact mass of the rubble pile before and after the collision, the kinetic momentum equation remains a heavily estimated variable. In planetary defense, an estimation is a structural vulnerability. This is the precise mandate of the European Space Agency's Hera mission. Launched in October 2024, the Hera spacecraft has spent the last 2 years silently traversing tens of millions of miles of deep space vacuum. Right now, moving through late 2026, it is executing its final, complex rendezvous maneuvers to match the orbital velocity of the Didymos binary system. It is arriving at the cosmic crime scene. Hera is not a blunt force impactor. It is a highly sophisticated orbital detective. Roughly the size of a small car, the spacecraft is equipped with a comprehensive payload of high-resolution optical cameras, thermal infrared imagers, and laser altimeters. As Hera inserts itself into a deeply complex chaotic orbit around the binary pair, it will systematically map the Dimorphos anomaly down to the resolution of a single meter. It will map the immediate vicinity of the impact zone down to a microscopic 10 centimeters. The scientific objective is to calculate a metric known as the beta factor. The beta factor is the mathematical measurement of momentum amplification. When DART struck the asteroid, it excavated millions of pounds of rocky debris. Because this ejector blasted backward into space, it acted like a rocket thruster, pushing the asteroid forward with far more force than the spacecraft alone could provide. The beta factor is the exact ratio of the total momentum transferred to the rock versus the initial momentum of the spacecraft. Think of a cue ball striking a cluster of loose chalk dust on a billiard table. The cue ball hits, stops, and the dust violently explodes in the opposite direction. The force propelling the remaining mass forward is directly tied to how much dust was ejected backward. To calculate the beta factor, Hera must measure exactly how much mass was blasted away. To do that, it needs to measure the crater. But the most consequential revelation awaiting Hera may not be the size of the crater. It may be the absence of one. Recent hydrocode impact simulations conducted by astrophysicists at the University of Bern suggest the dart impact was so violently energetic and Dimorphos was structurally so weak that a traditional bowl-shaped crater never formed. Instead, the entire asteroid simply absorbed the blow and physically warped. The impact did not carve a hole, it remodeled the entire celestial body. Hera is currently decelerating in the dark, preparing to illuminate the wreckage and finalize the exact equation for human survival. The Hera spacecraft is a massive, multi-million-dollar asset. It represents the pinnacle of European aerospace engineering, weighing over 1,100 kilograms. Because of its immense strategic value, it cannot risk diving too deeply into the chaotic, unmapped debris field, still lingering around the shattered Dimorphos moonlet. Hera is commanded to maintain a highly cautious standoff distance, hovering between 10 and 20 kilometers away from the binary system. But planetary defense demands intimate proximity. We cannot calculate the exact structural integrity of an asteroid from a safe distance. To bridge the gap, Hera relies on an entirely new architecture for deep space exploration, the distributed system. Hera is not traveling alone. Tucked inside its chassis are two autonomous nano-satellites, known as CubeSats, measuring just 10 by 20 by 30 centimeters, roughly the volume of a standard briefcase, and weighing exactly 12 kilograms each. These highly condensed machines will be ejected directly into the void. Think of Hera as the command ship. The CubeSats are the expendable drones. They are dispatched to navigate the highly dangerous, unmapped microgravity environment directly above the asteroid's jagged surface. The first CubeSat is named Juventus. Its objective is terrifyingly simple. It is designed to look through the solid rock. To achieve this, Juventus carries a highly specialized instrument named Jura. Once deployed, the briefcase-sized satellite will unfurl four 1.5-meter-long antennas, effectively transforming itself into a deep space ground-penetrating radar. Jura operates at a highly specific 60 MHz carrier frequency. This is not a standard communication wavelength. This specific radio frequency is designed to pass completely through the asteroid's surface, ignoring the exterior dust and penetrating the solid core. By flying a mere 3 kilometers above Dimorphos, Juventus will transmit these low-frequency radio waves directly into the bedrock. It is executing a detailed structural X-ray scan of a celestial body. The radar will peer up to 100 meters deep into the roughly 150-meter-wide moonlet. As the radio waves bounce off internal structures and return to the spacecraft, astrophysicists will construct a 3D tomographic image of the interior. They will mathematically confirm the rubble pile hypothesis, mapping the internal voids, the structural fault lines, and the density distribution that remain entirely hidden from our optical cameras. While Juventus maps the interior, the second CubeSat analyzes the exterior. This second drone is named Milani. Milani is commanded to execute a series of high-risk hyperbolic arcs, diving as close as 2 kilometers from the asteroid's surface. Because traditional circular orbits are mathematically impossible in such an extreme low-gravity environment, Milani must constantly fire its onboard cold gas thrusters, continuously altering its trajectory to prevent drifting away into the solar void. Milani carries a miniaturized hyperspectral imager known as Aspect. Unlike a standard optical camera, Aspect breaks down the sunlight reflecting off the asteroid into highly specific visible, near-infrared and shortwave infrared bands. It acts as a barcode reader for light. It will create a forensic mineral map of the dart impact crater, identifying the exact chemical makeup of the excavated material. Additionally, Milani carries a microscopic 5 cubic centimeter sensor named Vista. Operating on piezoelectric quartz microbalances, Vista is engineered to physically trap and weigh individual grains of dust still hovering around the impact zone. It can detect and analyze particles smaller than 10 micrometers, fractions of a millimeter across, searching for volatiles like water trapped in the rock. But the most consequential planetary defense data comes from how these three independent spacecraft communicate with each other. Hera, Juventus, and Milani will maintain a continuous S-band inter-satellite radio link. As they fly around the Didymos system, the microscopic gravitational pull of the two asteroids will subtly alter the speed of the three spacecraft. By tracking the infinitesimal Doppler shifts in these inter-satellite radio signals, scientists will map the total mass and extended gravitational field of the binary system to an unprecedented degree of accuracy. And when the primary mission concludes, the CubeSats will execute one final violent maneuver. They will not be retrieved. In June 2027, both Juventus and Milani will deliberately kill their thrusters and attempt to land directly on the jagged surface of Dimorphos. Because the gravity is incredibly weak, they will not simply touch down. They will crash. They will tumble. They will bounce. Their onboard accelerometers and gyros will record the exact mechanical resistance of those final tumbling impacts. By sacrificing themselves to the rock, the CubeSats will transmit the final pieces of the material science equation back to Earth. We will finally know exactly how the asteroid responds to kinetic trauma, right up until the tiny machines power down in the dark. The double asteroid redirection test was a catastrophic success, but in the strict architectural framework of planetary defense, a single successful collision is not a strategy. It is an anecdote. To protect the Earth from a 140-meter kinetic threat, we cannot rely on isolated anecdotes. We require a mathematical protocol. We need what physicists call scaling laws. Scaling laws allow aerospace engineers to take the data from a singular event, like a 600-kilogram spacecraft striking a 160-meter moonlet, and mathematically project those exact physics onto a radically different scenario. If a massive, dark anomaly is detected on a collision course with a populated continent, we will not be targeting a moonlet, we will be targeting a heavily armored, multi-million-ton monolith. To scale the DART experiment into a universal defense protocol, we need to solve a highly specific momentum equation. The missing variable in that equation is a metric known as the momentum transfer efficiency, frequently referred to by astrophysicists as the beta factor. The beta factor is the exact mathematical ratio between the initial momentum of the spacecraft we crash into the asteroid and the total final momentum that pushes the asteroid off its trajectory. Think of attempting to swing open a heavy, solid oak door. If you press your hand against the wood directly next to the hinges and push, you must exert an immense amount of physical force, and the door barely moves. Your mechanical efficiency is low. But if you move your hand to the farthest edge, near the brass handle, a light push swings the massive door wide open. Your efficiency is high. When we strike a city-killing asteroid, the beta factor dictates our mechanical efficiency. If the beta factor is mathematically defined as exactly 1.0, it means the asteroid absorbed only the raw forward momentum of the spacecraft. It behaved like a steel hammer hitting a lead anvil, but DART proved the beta factor for a porous anomaly is significantly higher than 1.0. Because the violent impact excavated massive amounts of regolith, and that debris blasted backward into the vacuum of space, the expanding cloud acted identically to a chemical rocket engine. The ejector did the heavy lifting. The efficiency was radically amplified. This precise amplification is the reason the Hera spacecraft is currently orbiting the Didymos system. By combining the exact post-impact mass of Dimorphos, the precise dimensions of the newly mapped X-ray crater, and the microscopic gravitational shifts recorded by the CubeSats, astrophysicists will finally lock in the definitive beta factor for a rubble pile asteroid. This single number is the structural keystone of planetary defense. Once we possess the definitive beta factor, we are no longer guessing. If the Deep Space Observatories detect an inbound kinetic threat, scientists will simply plug the asteroid's estimated mass into the scaled beta equation. The math will instantly output the exact mass of the interceptor we must build, the exact velocity it must achieve, and the exact coordinate it must strike to guarantee the necessary orbital deflection. Hera is not just conducting an autopsy on a space rock. It is writing the definitive mathematical operational manual for human survival. But this entire kinetic paradigm, no matter how flawlessly the math scales, is completely dependent on a single highly constrained resource. A resource that orbital geometry frequently denies us. The success of the double asteroid redirection test established a dangerous, unintended illusion. The public watched a spacecraft strike a celestial body and witnessed the orbital clock instantly change. It created the perception that if an asteroid approaches, we simply shoot it down. But planetary defense is not a tactical skirmish. It is a slow, agonizing marathon of orbital mechanics. To understand the fundamental limitation of a kinetic impactor, you must look at the exact velocity change achieved by the DART mission. When the 600-kilogram spacecraft annihilated itself against the Dimorphos moonlet, it did not stop the rock. It did not violently knock it sideways. Astrophysicists confirmed that the impact delivered a change in velocity, a metric mathematically known as delta V, of exactly 2.7 millimeters per second. To visualize 2.7 millimeters per second, watch a snail move across a sidewalk. The asteroid's trajectory was altered by the speed of a crawling insect. Against the cosmic scale, this is an incredibly consequential victory. But against the immediate threat of a city-killing asteroid, a microscopic delta V is entirely meaningless if you do not possess the single most vital resource in planetary defense: time. The kinetic impact strategy relies entirely on the geometric magnification of an angle. Think of firing a sniper rifle at a target 1 mile away. If the barrel of your rifle is bumped by a single millimeter right as you pull the trigger, the bullet leaves the muzzle almost perfectly on path. But as that bullet travels the full mile, that microscopic 1 millimeter angular shift drastically magnifies. By the time it reaches the target, the bullet misses by dozens of feet. An asteroid operates on the exact same geometry. If we impart a microscopic 2.7 millimeter per second delta V to a 160 meter kinetic threat, we alter its course by roughly 100 kilometers for every single year that passes after the impact. This is the tyranny of lead time. The Earth is a massive target. Our planet possesses a radius of approximately 6,370 kilometers. Therefore, if a city killer is on a dead center collision course and we hit it with a dart-sized kinetic impactor, we must push it a minimum distance equal to Earth's radius just to barely graze the atmosphere. At a rate of 100 kilometers per year, that requires a minimum of 60 years of advanced warning. 60 years. Even if we construct an enhanced, massive interceptor capable of delivering a much harder punch, the structural reality remains absolute. You cannot deflect an asteroid when it is close. If an observatory detects a 140-meter anomaly with only 3 years until impact, launching a kinetic weapon is mathematically futile. You will successfully strike the rock. You will successfully alter its velocity, and the asteroid will simply absorb the blow, drift a few hundred kilometers to the left, and still violently annihilate its target. To alter a trajectory, we must strike the rock while it is still hundreds of millions of miles away. We must hit it while it is crossing the orbit of Jupiter. But as we established in the opening chapters of this analysis, our sensor networks are failing to track tens of thousands of these exact threats. We are routinely discovering massive anomalies just days before they graze our atmosphere. When orbital geometry conceals the threat, and the tyranny of lead time renders our kinetic impactors entirely useless, humanity is stripped of its primary defense mechanism. We are forced to abandon the scalpel. We are forced to deploy the hammer. The fundamental math of a kinetic deflection is agonizingly simple: mass times velocity. But when the timeline collapses, that equation structurally fails. As we observed with the DART mission, a kinetic impactor requires years, or even decades, for a microscopic shift in velocity to geometrically magnify into a safe miss distance. But what happens when orbital geometry or a daylight approach conceals a city killer until it is less than a decade away? What happens if an anomaly like the Chelyabinsk meteor scales up, and our early warning networks only provide months of lead time? Astrophysicists at the Lawrence Livermore National Laboratory modeled this exact late response scenario using a conceptual kinetic spacecraft known as HAMMER. The data is unyielding. To deflect a massive kinetic threat with only 10 years of warning, which includes the time required to design the spacecraft, plot the trajectory, and execute the deep space flight, a single impactor is mathematically inadequate. The force required to push a massive rock off a collision course in such a compressed time frame would demand dozens of simultaneous, perfectly coordinated launches of heavy-lift rockets, each carrying a massive battering ram. Humanity does not possess that logistical infrastructure. We cannot build, launch, and coordinate a fleet of deep space kinetic weapons on a moment's notice. When an anomaly is detected late, the time required to slowly push the rock is gone. The mass required to forcefully ram the rock is too heavy to launch. We are stripped of our surgical tools, We must transition from transferring momentum to transferring raw, unparalleled energy. This leaves the global planetary defense community with a single, highly controversial alternative. We must deploy the most destructive force our species has ever engineered. We must rely on nuclear explosives. To the public, a nuclear defense scenario sounds like the desperate, chaotic climax of a Hollywood film. It sounds like an act of planetary panic. But in the sterile halls of aerospace engineering and national laboratories, it is a deeply serious, mathematically rigorous protocol. A nuclear device is not viewed as a weapon of mass destruction. In the vacuum of space, it is viewed strictly as an exceptionally dense, lightweight package of raw energy. A standard kinetic impactor requires a massive, heavy spacecraft to deliver a tiny physical punch. Conversely, a nuclear payload weighing roughly 550 kilograms, a mass easily carried by modern rapid launch rockets, can deliver an explosive yield measured in megatons. It completely bypasses the limitations of launch weight and flight time. If a city-killing asteroid emerges from the sun's blind spot with only months to spare, kinetic math fails. The physics dictate that humanity will have no choice but to strap a nuclear device to a high-speed interceptor and fire it into the dark. Detonating a nuclear weapon in the absolute vacuum of deep space does not operate on the physics of terrestrial warfare. There is no air. There is no shockwave. The mechanics of a cosmic nuclear strike are completely alien to anything we have ever tested on Earth. When popular culture imagines a nuclear strike against an asteroid, the visual is always the same. A missile plunges directly into the rock, detonates and blows the massive anomaly into a billion glowing pieces. But Hollywood relies on the physics of terrestrial warfare. In the total vacuum of deep space, an explosive detonation operates under completely different mechanical laws. There is no air, there is no atmospheric shockwave, there is no concussive blast. If you detonate a thermonuclear warhead in the dark, you do not get a sprawling fireball or a mushroom cloud. You get a blinding, near-instantaneous flash of raw electromagnetic energy, predominantly high-energy X-rays, gamma rays, and prompt neutrons. Therefore, the objective of a late-stage nuclear defense protocol is strictly not to shatter the rock. Attempting to blow up a city-killing asteroid from the inside out is mathematically chaotic and structurally dangerous. Instead, astrophysicists rely on a highly calculated maneuver known as a standoff detonation. The interceptor spacecraft is programmed to fly alongside the massive kinetic threat and intentionally detonate the nuclear device a specific distance away from the surface. This is where the physics of nuclear ablation take over. When the warhead detonates, a massive wave of X-rays and gamma radiation radiates outward at the speed of light. This energy slams into the asteroid's facing side. Because the rock has no atmosphere to buffer the radiation, the sheer intensity of the X-rays instantly superheats the outermost layer of the asteroid's surface. The rock does not melt, it does not burn, it flash vaporizes. Within microseconds, tons of solid rock are violently converted into a superheated, rapidly expanding plasma gas. This sudden vaporization triggers Sir Isaac Newton's absolute law of motion. As this superheated gas expands and blows violently outward into the vacuum of space, it exerts an equal and opposite physical force on the asteroid itself. The vaporized rock becomes a thruster. We are not using the bomb to push the asteroid, we are using the bomb to force the asteroid to push itself. By ablating the surface, we temporarily turn the dead rock into a massive, uncontrolled rocket ship. The sheer violence of the expanding gas acts as a massive kinetic kick, altering the rock's trajectory with significantly more force, and in significantly less time than a standard kinetic impactor ever could. It is the single most powerful deflection mechanism humanity can mathematically engineer. But this unparalleled raw power carries an unprecedented risk, because we are delivering an astronomical surge of energy to a completely unmapped, potentially fragile anomaly. The difference between saving the Earth and sealing its fate comes down to a margin of error measured in meters. The ultimate goal of a nuclear standoff detonation is precise, controlled deflection. But precision requires an intimate knowledge of the target's internal architecture. If we miscalculate the structural integrity of the anomaly, the defense protocol fundamentally collapses. We trigger the shotgun effect. Astrophysicists at the Lawrence Livermore National Laboratory have extensively modeled these exact high-stakes scenarios. They analyze the mathematical threshold where a controlled push transforms into a catastrophic disruption. The dividing line is purely structural. Recall the rubble pile revelation. A significant percentage of city-killing asteroids are not solid, metallic monoliths. They are fragile, loosely bound aggregates of gravel, dust, and massive internal voids. When the intense X-ray pulse from a nuclear detonation flash vaporizes the exterior, the expanding plasma exerts an immense mechanical shockwave deep into the rock. If the explosive yield is calibrated too high, or if the internal bonds of the rubble pile are too weak, the asteroid cannot absorb the trauma. The microscopic gravity fails. The bedrock fractures. In the calculus of planetary defense, this is the worst-case mathematical outcome. We have not destroyed the kinetic threat, we have simply multiplied it. By inadvertently exceeding the anomaly's structural limit, we transform a single, mathematically predictable cannonball into a sprawling, unpredictable shotgun spray of hypervelocity shrapnel. We trade one target for thousands. Instead of a single massive airburst localized over a specific longitude, the fragmented pieces spread out along the inbound orbital path. Many of these fragments remain large enough to bypass atmospheric disintegration. They rain down across multiple continents simultaneously, triggering a rolling barrage of regional detonations, magnified by the unprecedented complication of radioactive debris falling into the upper atmosphere. This is exactly why the material science data gathered by the Tianwen-2 and Hera missions is mathematically non-negotiable. To safely execute a nuclear ablation, aerospace engineers must calculate the exact megaton yield required to move the rock, while remaining strictly below the threshold that breaks the rock. They are forced to tune a thermonuclear weapon like a surgical instrument, but calculating the exact explosive yield is an engineering problem. Executing the launch is a legal one. When humanity is staring down a city-killing threat, the greatest barrier to survival is not the laws of physics, it is the laws of international governance. When a civilization faces an extinction-level kinetic threat, we naturally assume that science will dictate our survival. We assume that if the mathematics demand a nuclear ablation to deflect an incoming city killer, the rockets will simply launch. But planetary defense does not operate in a sterile vacuum. It operates within a rigid, deeply entrenched framework of international law. If humanity attempts to launch a nuclear weapon into the dark, we immediately trigger a catastrophic geopolitical gridlock. The barrier is not a lack of aerospace engineering. The barrier is the Outer Space Treaty. Drafted during the height of the Cold War and entering into force on October 10, 1967, this foundational document governs the activities of nations in the cosmic void. The substance of its arms control provisions is explicitly outlined in Article 4. It is mathematically unambiguous. The treaty legally binds member states not to place any objects carrying nuclear weapons in orbit around the Earth, not to install such weapons on celestial bodies, and not to station them in outer space in any other manner. If a sovereign nation straps a 550-kilogram thermonuclear warhead to a deep space interceptor, they are scientifically saving the planet. Legally, they are weaponizing the heavens. Furthermore, the legal constraints do not end at the launch pad. Even if a nation successfully bypasses the Outer Space Treaty, the physical act of detonating the ablation device triggers an entirely separate cascade of legal violations. The Partial Test Ban Treaty of 1963 expressly prohibits any nuclear explosion in outer space. This prohibition was heavily reinforced by the Comprehensive Nuclear Test Ban Treaty, CTBT, adopted by the United Nations General Assembly in 1996. The CTBT bans all nuclear explosions, for both civilian and military purposes, in all environments, without exception. It does not matter if the objective is planetary defense. The law recognizes no difference between an act of cosmic deflection and an act of unprovoked aggression. This creates an unprecedented structural dilemma. Think of a massive commercial airliner hurtling toward a densely populated city center. The pilot has locked the cockpit door. The only way the passengers can prevent the crash is by violently breaking the door down, an action that is strictly, legally prohibited under federal aviation law. Do you break the law to survive, or do you follow the rules and die? When an asteroid is detected with only months of lead time, we face the exact same impossible choice. If the United States, Russia, or China detects a city killer and independently launches a nuclear interceptor without global consensus, it could instantly trigger a terrestrial nuclear war. A rival nation tracking a heavily armed, classified rocket screaming into the upper atmosphere cannot visually verify if the warhead is aimed at an approaching asteroid or if it is dropping toward their capital city. To prevent this fatal miscalculation, planetary defense protocols require the United Nations Committee on the Peaceful Uses of Outer Space, COPUOS, to coordinate a unified global response. Originally established in 1959, COPUOS now comprises over 100 member states, each possessing their own geopolitical interests. If a kinetic threat is identified, the international community must collectively agree to temporarily suspend the Outer Space Treaty. They must draft emergency resolutions. They must negotiate absolute transparency. But diplomacy requires time. Bureaucracy moves at the speed of consensus. An asteroid moves at 18 kilometers per second. By the time the global superpowers finish debating the legality of saving our species, the window for nuclear ablation will have permanently closed. The math will fail, and humanity will be forced to transition from preventing the impact to simply bracing for the shockwave. When orbital mechanics defeat us, and the window for kinetic deflection or nuclear ablation permanently closes, planetary defense ceases to be an astrophysics problem. It becomes a localized emergency management crisis. If a city-killing asteroid slips past our deep space networks and is detected just weeks before impact, we must abandon the sky. We must focus entirely on ground-level survival. For over a decade, NASA and the Federal Emergency Management Agency, FEMA, have conducted extensive tabletop exercises simulating this exact structural failure. The primary objective in these simulations is to rapidly calculate a geographic metric known as a risk corridor. Because telescopes cannot instantly pinpoint the exact geographic coordinate where the rock will strike, mathematicians draw a massive line across the globe representing the asteroid's potential impact footprint. As the impact date approaches and the telemetry data sharpens, the corridor narrows. If this highly lethal corridor localizes over a major metropolitan area or heavily populated coastline, the protocol dictates only one option. We must issue a mandatory mass evacuation, but an evacuation order is a piece of paper. It is an administrative decree. It does not alter the physical limitations of terrestrial infrastructure. Modern highway systems are entirely incapable of supporting the instantaneous, panicked exodus of tens of millions of people. To understand the lethal mathematics of mass migration, we must examine the structural collapse that occurred ahead of Hurricane Rita in September 2005. Faced with vivid warnings of catastrophic storm surges, approximately 2.5 million residents in southeastern Texas attempted to flee simultaneously. The sheer volume of vehicles instantly overwhelmed the interstate system. A standard 3.5-hour drive transformed into a 24-hour, bumper-to-bumper standstill in suffocating 100-degree heat. The logistics failed entirely. Extended idling caused massive fuel shortages, stranding countless vehicles on the highway. Ambulances and emergency medical responders were physically trapped in the gridlock, completely unable to reach individuals suffering from heat stroke, insulin depletion, or cardiac arrest. When the disaster concluded, the data revealed a terrifying paradox. The high winds and coastal surges of Hurricane Rita directly killed 6 people. The evacuation process itself killed 107. The attempt to survive became the primary vector of mortality. Now, scale that logistical collapse from a slow-moving hurricane to a hypersonic kinetic threat. A hurricane offers days of warning, and the worst-case scenario is deep water and structural wind damage. An asteroid impact guarantees an instantaneous, unsurvivable megaton airburst, generating thermal flashes that incinerate infrastructure and overpressure waves that flatten city grids for hundreds of miles. The resulting panic would be absolute. If NASA projects a risk corridor stretching from Pennsylvania to the Atlantic coast, as they did in their 2013 tabletop exercise, and issues a 72-hour mandatory evacuation order, the highways will immediately freeze. Millions of citizens will become permanently trapped in their vehicles directly inside the blast radius. We must strip away the illusion of ground-level resilience. If an asteroid is allowed to reach the lower atmosphere, the battle is already over. The terrestrial evacuation protocol is not a solution. It is simply a desperate, lethal arithmetic. We either alter the trajectory in deep space, or we accept the casualties. In November 2025, humanity crossed a quiet, mathematically terrifying threshold. The global astronomical community officially catalogued the 40,000th near-Earth asteroid. To understand the sheer volume of kinetic traffic in our immediate orbital neighborhood, you must look at the timeline. It took over a century, from the discovery of the first near-Earth asteroid in 1898 to locate the first 15,000 objects by 2016. We reached 30,000 by 2022. The last 10,000 anomalies were discovered in a violently compressed span of just 3 years. The solar system is not becoming more crowded. We are simply waking up to the reality of the shooting gallery. Earth is a massive target. It travels through the vacuum of space at roughly 67,000 miles per hour. We are blindly sailing through a localized ocean filled with tens of thousands of dormant, unmapped kinetic mines. The only thing standing between the continued functioning of modern civilization and a devastating hypersonic airburst is the silent, automated vigilance of a handful of telescopes staring into the dark. This is the Long Watch. Every single night, networks like the Asteroid Terrestrial Impact Last Alert System, or ATLAS, execute an unprecedented global sweep. Operating a network of automated telescopes spread across the globe, ATLAS does not stare at a single point in the sky. It aggressively sweeps the entire observable darkness, scanning the whole visible sky multiple times per night. The system captures tens of millions of pixels every 30 seconds. It filters the atmospheric noise, it ignores the stationary stars, it hunts exclusively for the microscopic shifting pinpricks of light that do not belong. When the sun sets, the shutters open, the machines do the math, the data flows. But as we have established throughout this analysis, our optical networks possess a catastrophic structural blind spot. They cannot see the threats hidden within the sun's glare. They cannot instantly calculate the precise material science of a rubble pile asteroid. They cannot manufacture the decades of lead time required for a successful kinetic deflection. Planetary defense is not a problem we have solved. It is an active, ongoing structural emergency. We are transitioning from passive observers to active participants in the orbital mechanics of our solar system. Missions like Hera, Tianwen 2, and the upcoming NEO Surveyor are the architectural foundation of our survival. They are the tools we are building in the dark, hoping we finish them before the math finally catches up with us. We scan the sky. We refine the models. We wait for the pixels to move.